Hey everybody, welcome to this edition of Welding Wednesday. This week we're going to be talking all about filler metals. If I sniff a lot, sorry, it is winter time. Table of contents. So we're going to talk kind of what are filler metals, what do we use them for, how do we classify them, how do we go about selecting them, some advances in filler metals, and then some challenges. So intro to filler metals. What is a filler metal? So filler is the material added during welding to join two pieces of metal. If you remember from, 2 or 3 Welding Wednesdays back, we talked about what makes welding different than other joining processes. And with welding, you're taking multiple pieces of base metal, usually combining it with a filler metal, and then you're making a brand new, like, single object. So you're taking multiple pieces of metal and putting it together to form one piece of metal. When you do that, and if you just use the base metal, that's called autogenous welding, which is one of my favorite $5 words. But with autogenous welding, because of changes like in metallurgical characteristics, it can really affect like mechanical properties, that sort of thing. So that's where filler metal comes in. So filler metal provides strength to the joint. It adds a lot of it can add a lot of different alloying elements. It can make sure that the joint is clean from contamination, things like that. It also fills gaps and ensures weld continuity. So it makes sure that the weld is consistent all the way through and it has like a nice transition between the base metal and then your weld bead. That's really important because anytime there's like sharp angles, that's places where you can like focus stress or force and possibly break whatever you're trying to put together. A key consideration when we're trying to figure out what type of filler metal to use is we need to have one that's compatible with the base metal. So for instance, if we're doing steel, just regular steel, we don't want to use aluminum for a bunch of reasons. Main one is they're dissimilar metals, so their structure is very different. And so that means that they like expand, contract, all those things differently. And basically, they're like little cell structure inside. It's called a unit cell, which we'll talk about later when we get to metallurgy, probably a few months on from here. But those unit cells are different shapes, so they just can't fit together very well to form a crystal. So I've before been like TIG welding and grabbed, I think I was doing stainless, and grabbed some aluminum rod. This is right when I was starting out, and I didn't know the difference between anything. And so I was able to melt them all together. But the moment I took off the amperage and it started to cool, it just went and like broke apart. And that's because of the different cooling rates between the stainless steel and the aluminum. We can weld the similar metals, but only if we do something that has like a tremendous amount of force. So things like explosive welding, you can do it like, I think, percussion welding on a very small scale. You can use magnets on a small scale, like that sort of thing. But overall, we want to make sure the filler metal is a good match for our base. All right, let's keep moving. So filler versus electrode, you'll hear these words all the time. Some people use them interchangeably, but they do both describe something in particular. So your filler metal is consumable. It's added to the weld and joins the two pieces of metal, and it becomes part of the weld. An electrode conducts electricity to create the arc that we use for arc welding, and it can either become part of the weld, well, that's where it's consumable, or it can be non-consumable. So consumable electrodes are stick electrodes, MIG electrodes, TIG electrodes, stick, MIG, and flux core electrodes. Non-consumable is your TIG electrode. So if we think about it, when we use electrode for SMAW, a stick rod, when we use our wire for GMAW, our flux core wire, all of that melts, becomes part of our final weld. With GTAW or TIG, we have the tungsten electrode, which we use to provide heat to our metal and melt everything. And then we'll add in additional filler metal with usually our other hand and feed it in separately. So that's where they're two separate things. So a filler can be an electrode, Electrode can also be filler, but they're not always the same thing. All right, what are some functions of our filler? So, structural integrity provides mechanical strength to the weld. You can have fillers that have many different alloying elements to change your strength. It can change toughness, things like that with the your weld joint. Corrosion resistance, so protecting against the environmental and chemical exposure. Things like Core-10 or weathering steel, you have to use a particular type of filler to make sure that you are getting enough of like a mix of the Core-10 and the filler so that the weld joint will like corrode at the same rate as the base metal, like it's supposed to do. Because if you have Core-10 and then your joints all rust out, not really useful at all. So that's something there to think about. Ductility and toughness. So ductility is the ability to be stretched into like a wire without breaking. Toughness is the ability to like withstand an impact without like major deformation. So a lot of times if you're going to like increase ductility or toughness, you'll have a filler that might have like chrome added to it, or chromium. Filling and bridging, so it helps to join components with gaps. So if you're doing like an open root weld, you have that gap in there, you want the complete joint penetration, we'll use our filler to actually fill that gap before we go ahead and finish filling out the entire joint. And then finally, metallurgical influence. So that's kind of similar to the structural integrity, but it can change that final composition and the properties of the weld. If we do a weld on steel correctly, the weld should always be stronger than the base metal. Base metal should break first. And so part of the thing of figuring out what type of filler to use is making sure that we can match the right strength characteristics to ensure that we're not going to break on our weld, we'll break in the base metal. All right, types and classifications. So starting off, we have our flux-covered electrodes or stick rods. We can see here in these photos, first one kind of is showing what happens when you strike your arc and start melting your electrode. So quick refresher, your electrode starts to melt, the interior core wire, it becomes little drops and they go down, and that's what creates the weld joint. Your flux covering melts, your flux goes into the molten metal, and it also creates a fume cloud to go and protect it, shielding gas, so to protect the molten metal from the atmosphere. And then as it solidifies, that flux rises to the surface of your weld bead as slag. It'll go ahead and help to slow cooling, and will help to make sure that it's like picking up a lot of corrosion, things like that could otherwise jeopardize the integrity of a weld. It can pick up a lot of that contamination or whatnot and bring it up to the surface. So kind of talked about this already, but yeah, core wire, it carries your current. Most of the filler metal is from the core wire, and then it supports that flux. Flux provides some alloying elements, stabilizes the arc, insulates that core wire. If you've ever tried to like stick weld with electrodes that have like chipped flux coating, very difficult, because what will happen is that area, since it's not insulated by the flux, it'll start to like heat up when you're putting an arc through it. So you're going to have less like amperage going to the weld, but also you'll have like this spot in the electrode that's heating up and like can melt and whatnot. So it's very difficult to actually weld very well if you have an electrode that has a bunch of like flux missing in the middle of it. Provides that slag cover to protect the weld, slow the cooling, slower cooling, less brittleness, and then again provides a shielding gas. When we're classifying our stick rods, we'll use the AWS classification, so that's the American Welding Society classification, and everything means something. It's not just random. So we'll look at a very common stick rod here would be 7018. So full classification of this particular example is E7018-1 H4R. So going through it piece by piece, the E means electrode. So that's telling us this is going to carry electricity, or it can carry electricity. The 7 and the 0 is the minimum tensile strength if you weld it correctly. So this is in KSI, or 1,000 pounds per square inch. So if you weld everything correctly, you should not be able to basically tear it apart with less than 70,000 pounds per square inch of force. Welds are crazy strong if you do them correctly. One is position. So in this case, 1 means all positions. So we can weld in the flat, horizontal, vertical, and overhead. You can have a 2, which is just flat and horizontal. I don't think there's a 3, and then I believe there's a 4, which is like vertical down. You can fact check me on that one. And the 8 is the type of coating and current. So that's going to tell you what polarities they can run at, and then what the coating is. An 8 is going to indicate a low hydrogen coating. The -1 means it meets lower temperature impact requirements. So basically, it's been tested that if you are operating at a lower temperature, I believe it's tested at negative 20 degrees Fahrenheit with what's called a Charpy V-notch test. And it just measures how much it's going to move or break at that temperature. So when you have a 7018-1, it's been tested to be able to be used in lower temperature service. The H4 is going to be what our hydrogen levels are. So here H4 is less than 4 milliliters per 100 grams of hydrogen. And then the R is meet requirements of absorbed moisture test. So they did a test, and it'll have a certain amount of moisture in it when it leaves, like the factory. Why is this important? Especially with this type of rod, is hydrogen is like our real, not enemy, but it's the thing that causes the most issues with our welding as far as like outside gases are concerned. Last week, I believe we talked about industrial gases, or last time, whenever you're watching this. And so hydrogen is the smallest element. So it has, or I should say it's number 1 on the periodic table. So it's the smallest atom. And because of that, when we go ahead and heat up metal, those unit cells that I was talking about previously, they move apart. That's what causes the metal to go from a solid to a plastic state and then a liquid. And as they're moving apart, there's like more room between them. And since hydrogen is such a tiny little atom, it can just scoot right on in there. And then once it solidifies, if the hydrogen has not had a chance to be removed, then it's going to get trapped. And you're going to get what's called cold cracking or underbead cracking. There's some types of welding that are done like in shipbuilding, where you'll actually do your welding and then they get inspected like 2 weeks later, because that's how long it can take for that crack to develop from trapped hydrogen. So not having hydrogen, really big deal. And that's also why we have the absorbed moisture test, because moisture has hydrogen in it. So it's not like exactly the moisture that's the big issue. It's the hydrogen component of the moisture. Some other notes on the classification. We see here on the left side where it goes through some of those rods you might have heard of already, 6010, 6013. We just looked at 7018, 7024. There's 8018, there's 11018, there's all sorts of stuff. And then it talks about the type of covering, what position you can weld in, and then the type of current. So if we look at 7018, right down here, see if I can figure out how to use my pen. Oh yeah, nailing it. So it's a low hydrogen rod with potassium and iron powder. Iron powder is usually used to increase deposition rate, so you're getting more filler into your joint. Says that we can use it flat, vertical, overhead, and horizontal. Not vertical down. This is really meant to do vertical up. And then it can run on AC or DC. And then reverse polarity. So pretty good as far as like what it can do for you. This is why it's kind of like a really common rod to use. Wire tight fillers. So main 2 we're going to look at is like our wire that's on our spools for GMAW, and then wire that's used for TIG, so our straight links. This is solid wire. Upper right, we see a little picture of like what it looks like with GMAW. So this is where we're squeezing the trigger. Our wire comes out. Electricity is going along our wire and being conducted into the weld and to make the arc. And then we also are dispensing shielding gas to protect the weld. For this other photo down here in lower left, we have a tungsten electrode that's providing the heat and the arc to melt our base material. And then we have that filler rod coming in usually with our other hand, and we're dipping it into our molten weld pool. Looking at the classification for wire type filler metals, we can see at the beginning we have an ER. So we already know E, that's electrode, and then R equals rod. So this means that this type of filler can conduct electricity, or it can be used just as a filler rod by itself. This is important and great to know, because when you, let's say you have a customer or you're somebody who's welding, and let's say you have like 70S-2 and you're doing some TIG and you run out and you're like, oh man, I gotta get a hold of my distributor or trying to go to the store, everything's closed, but you have a spool of 70S2 for MIG, you can go ahead and just cut some length right off that. Same thing. Tensile strength is again the next two numbers here, the 70. So again, it's minimum tensile strength. So minimum of 70,000 pounds per square inch to tear this apart if you follow directions and weld it as the manufacturer tells you to. S equals solid, so solid wire. And then -3, same thing as like suffixes previous, chemical composition, shielding gas, that sort of thing. I would say the two most common like MIG wires that I've seen used, and also TIG, is a 70S-2 and 70S-6. And I can't remember off the top of my head exactly what the difference is. I believe the -2 you can use for things that have like more corrosion. It's just like you can use it with not as clean metal, like things like that. So okay, moving on into cord type filler metals. So both these photos here are showing the flux core process. So we have two types, self-shielded flux core and then dual shielded flux core. So with self-shielded flux core, it's basically like MIG and stick kind of like put together. The electrode for your flux core is like a flux electrode for stick inside out. So instead of a core of metal surrounded by flux, this is a core of flux surrounded by metal. I recently took a trip, a couple months ago now, to Cleveland, to Lincoln Electric, to do some training, and they make all their flux cord wires there, and it was so awesome to see how they make them. Talk about that more in a second. And then on the right-hand side here, right above my head, that's a dual shield flux core. So the electrode's the same. We're going to have like an inside-out stick rod, and then we also have additional shielding gas to provide more protection. Here's a picture of what a flux core kind of looks like. There's a couple ways to make it. This is probably the most common, where we're going to have flux in the middle, and then we have like a flat piece of metal that has been turned and closed and made into a circular shape. When we're looking at our classifications for flux core, similar things to what we've seen already. So E is electrode. Here, the first number is your minimum tensile strength. So here's an example here. Instead of your tensile strength being like 70 times 1000 psi, for flux core, it's the single digit. So here it's an 8 times 10,000 psi. So the minimum tensile strength for E81 T1 is 80,000 pounds per square inch. The 1 is position, so similar to what we did with stick, though. Notice here, 1 is all position, that's the same as it is for stick, but 0 is flat and horizontal, which is different than with stick, where 2 is flat and horizontal. T is flux cored electrode. So if you don't remember anything else, if you see like a classification like this and you see a T, flux core, know it right off the bat. Next one is gas type, usability, performance, that sort of thing. And then we have various suffixes that mean different stuff. So different types of gases to use, hydrogen ratings like the 7018, impact ratings like the 7018-1, all that sort of stuff. You'll see here that the flux core is like a little more complicated, like it has more options and more things that can be in the entire like string of description. This is because you can get much more like granular with flux core as far as mixing different types of filler and flux together to get a particular result. Mm-hmm. For classifying our filler metals, we have like the classification names that we looked at, but then they also fall under like 4 different, or I should say like 3 different reasons to use it. So like the first one is composition based. So is our filler going to be used for carbon steel, stainless steel, aluminum, low alloy steels, whatever you're going to be doing? Or it's form based. So do we have solid wire? Do we have flux cored wire? Do we have coated rods? Do we have bare rods? We can group things that way. We can group them according to their classifications for codes. So AWS, we already talked about, American Welding Society classification. That's what we're going to use for almost everything. ISO classification, so that's an international standard. That's another classification that exists. Like 7018 is our AWS classification, but there is also a corresponding ISO classification for that. And then the importance of all that is we want to select the right filler metal for our specific applications. So classification versus specification. You might hear specification out there in the world also for your filler. So classification, if we run down this chart real quick, it's going to tell you a specific filler, 7018, going to focus on the mechanical chemical properties. So, low hydrogen, the impact test, that sort of thing. Some examples we looked at already, 7018, 70S-6, Thoroid L, that's a stainless steel rod. Level of detail, so it's going to provide a lot of performance characteristics when you get like granular down into what the different additions and all the different classification like numbers, letters mean. If we look at a specification, that defines a group of similar filler metals. So there can be multiple filler metal types under that standard. The American Welding Society standards for like carbon steel electrodes is A5.1, for stainless steel A5.9. So it provides like an overarching testing and manufacturing guideline. So when like a company like Lincoln or whatever is manufacturing, let's say 7018, they have to make sure that they're manufacturing to the specification, which is A5.1, and then also meeting the classification requirements in terms of low hydrogen and any alloying elements that's in 7018. This is important to know because any of you who are going to work with specifications or code books or anything like that, you'll see that when we have like a WPS or a welding procedure specification, there will be a part where it talks about like the welding classification and specification to use. And you have to match like your different groups of filler metals with different groups of base metals, that sort of thing. So it's just important to know that specification and classification are 2 different things, and they apply to 2 different aspects of your filler. All right, how do we go ahead and select our filler? First one we already touched on base metal compatibility. Want to make sure that we have a similar metal unless we're doing dissimilar welding on purpose. And then we want to make sure it's a mechanical match. So, the codes for like structural steel say that your filler has to have at least the tensile strength of your base metal. So if we look at a common base metal like, I don't know, AISI 1020, like pretty common mild steel, don't quote me on this again, but I want to say like the tensile strength is like, it's like 60,000 maybe or less. So that's why something like a 70,000 rod or, like a 7018 or 70S is good to use if you're doing structural steel welding, because done properly, like I said before, the joint will be stronger than the base, which is what you want. You got to pick a filler that can suit a particular welding process. So MIG, TIG, stick, whatever. If you want to stick weld and you have straight lengths of TIG rod, not going to happen for you very well. Joint design, so the thickness and the position will help to determine which type of filler. Again, with stick rods, talk about 70-24. That lays down a lot more filler. It's a fast fill rod, they call it. But because of that, because it's putting out a lot more filler, the filler's molten longer, so you can't use it outside of a flat or horizontal position, or it'll just like fall down on you. So if you needed to weld up real big joints overhead, 70-24 would be awesome because it'll help you fill it up faster, but it won't work because it's too liquid and it's just going to fall on you. So, you're going to have to do a bunch of passes with 70-18 or something like that to be able to fill that up correctly. And then, does it meet our standards? So are we welding to AWS code, ASME, which is Society of Mechanical Engineers, ISO regulations? Like, what are we welding to? Does it meet that code or standard that we are meant to make sure we fill? If we break it down for base metal a little bit, just again to see how we can make our decisions, we look at carbon steel. Let's look at stick. 7018 common classification. A common name would be Excalibur. What I really want you to pick up on this is that classification and like the common name are not like the same thing. And by that I mean 7018 in Lincoln could be called is called Excalibur, one of the types. If you use Washington alloy, it's called like Eagle Strike. But you look at the spec sheets, it's the same type of 7018. It meets the same classification and specifications. So this is important because if you're using a particular like brand of rod, you really like the brand, but maybe you can't get it, or maybe you want to switch to another brand. The brand names are the brand names, right? Excalibur is your brand name. If you want to switch to Washington alloy, okay, cool, Eagle Strike, but it's still the same 7018. And that's what's important, because that classification has to be standardized so you get the same results. Everything kind of hinges on being able to get the same results over and over again, no matter what type of 7018 you use. But people definitely have their preferences. Stainless steel, example of a stainless steel like common name is OK TIG rod from ESAB. Aluminum super glaze, that's a Lincoln common name. And then classification ERNICRMO3-3. So that's electrode rod for nickel, chromium, and molybdenum. Common name is Inconel 625. So Inconel is a common name for that type of mix of elements. So yeah, just make sure that when you're picking your rods, when you're trying to figure out what type of filler to use, understand that different types of companies, different like common names or brand names, just check those spec sheets. It's important to check the spec sheets, make sure it's meeting all the requirements of the particular classification you need. And if we're trying to find what type of filler to use, which I'm not going to lie, is probably like, I don't know, a quarter of the questions I get here at MO2 is trying to figure out what type of filler. A lot of times that's going to be, if you're definitely doing like code work or WPS work, a lot of times engineers are going to help figure that out. But I can help insofar as, hey, I'm welding stainless to mild steel. What would be a good pick? Something like that. Again, running it through the same type of like selection process I previously laid out. What is it going to be used for? What are the conditions that the final weld will be subjected to? High heat, very cold, moisture, whatever. Position, welding process, all that sort of thing. And then I refer to things like this. So this is an awesome chart. I love a good chart from Hobart for aluminum filler metal. So we can see right above my head over here, you basically have your base metal that you would pick. Then you have a filler metal, and it kind of helps you, it breaks it up into categories and then like rates it. So rates it on cracking, strength, ductility, corrosion, temperature rating, color, post-weld heat treatment, or post-weld, pre-weld. It's one or the other. And then toughness. So two very common aluminums that are used for filler are 4043 and 5056. So if we look at just what are the difference there, 4043 flows really well, has more silicone in it, so flows better than the 5356, but it's not as strong. 5356 has a much higher strength, but it is more sensitive to cracking because of that higher strength. 4043 does not anodize, so if you're anodizing your welds, not going to work for you. 5356 does. So when somebody comes to me and says, hey, I am welding aluminum, I want to know, should I use 4043 or 5356? The first thing I always ask them is, are you going to be anodizing it? Because then right away we can figure it out. 5356 if you are going to. If you're not, then we can get deeper into, okay, what are the strength requirements? Who's welding it? If it's for a school and you're learning how to weld aluminum, I would be more inclined to suggest a 4043 because it just flows a lot smoother. I think it's simpler for a lot of people to learn how to use, that sort of thing. All right, bringing it home here. So some advances that have been coming out in filler, more high strength, lightweight filler materials. Well, new things are getting invented all the time. Super exciting. Companies are coming out with new types of blends. Always looking for a way to like meet performance with cost, that sort of thing. Advances in coatings, alloy formulations. So what type of different elements can we use? Copper-free things are gaining more popularity. Humans taking in a bunch of free copper is not great. So, trying to find different ways that we can coat our wires, things like that. And then using digital tools and AI for filler metal selection. So, instead of calling me and having me figure it out for you or offer suggestions, digital tools and AI can start to do that. Without any of that, though, it just takes time to make sure that it's trained correctly and that it's giving you the right answer. So even if you are using like AI, which I use AI all the time, like ChatGPT to do stuff, because it's so convenient to help me get started. And that's what I think it's good for, is to get you started. So you can be like, hey, let's go get ChatGPT. I'm welding stainless to mild steel. I'm using GTAW. What filler would you suggest? It'll present to you some fillers. Then it's up to you to just verify. If it says 309, look it up, look at your spec sheet. Yeah, that's good. Go from there. I love spec sheets. And finally, challenges. Some challenges that we find with our filler and just kind of the industry overall. Specialty metals are very expensive. Titanium, nickel alloys, things like that, with different types of geopolitical things. So we got tariffs, we have conflict, those sort of things that will all affect supply chain, which is point number 2 here, which can make these specialty alloying elements much more expensive and therefore really rising the cost of filler, or perhaps getting even to the point where they're not available anymore. Filler metal mismatch, weld failure, so that's using incorrect metal selection, things that, again, are not, they don't have enough of the similar characteristics, so they're not going to combine properly. Using a filler that is for the wrong position, things like that, can lead to cracking, all sorts of different problems. So you can look at the top photo there. There's a good picture of a crack from something that was improperly done. And then operator training skill level. This is one people don't know a lot, but depending on your type of filler, it actually can be very difficult to weld, like skill-wise. So from personal experience, I had to do some Inconel stick back in the day, and that stuff is like super runny. I don't know what other like to say it. It's like super runny, and then the slag that's left over is incredibly hard, like incredibly hard. So Inconel is very hard to grind. It's a very tough material. So if you are having trouble with welding, you got this drippy stuff, you're welding in out of position, you have this drippy metal going down and maybe falling over this extremely hard to remove slag, like you're running into a lot of issues where you can get that entrapment in there. The inclusions going to have poor quality weld. So the welder's skill is actually a really big deal in being able to like overcome the differences in the rod. Another thing is like if we think about 7018, welding larger diameter 7018 out of position definitely has, is a skill thing. You can usually weld with larger diameter rods out of position if you have more history and skill with using the stick rods. So yeah, training and skill does matter. All right, I think that's it. So again, here's some selection of the resources that were used for this presentation. And as always, if you need anything, please reach out to me. Please reach out to MO2 directly, and we want to help you. So give us a holler. All right, thanks again, and see you next time.